All right. So we have another way to identify thermodynamic parameters for a given chemical reaction or for given bonds, and that is by using our tabulated bond energies. All right. So because the energy in a chemical is stored where, Fred?
Oh, what?
The energy that's stored in a chemical, where is it? Where's that energy at?
Oh, you mean it's in the bonds?
That's right, it's in the bonds. Because when two atoms come together and form a bond, they stabilize each other's electron configurations, and that energy is released to the surroundings, all right? Now, good opportunity to do a little review. When bonds are formed, is energy released or required, or it depends on the kind of bond formed? Now, you folks at home think about this answer too. This needs to be one that you take with you to your dying day or throughout the eternities, because the same principle will apply throughout the eternities. What do you think, Fred?
What was the question again?
When a bond is formed, is energy released? Or when a bond is formed, is energy required? Or when a bond is formed, it depends on the kind of bond on whether it's required or released.
Oh, I remember this. When a bond is formed, energy is always released.
That's right. Energy is always released. So we have a list of bonds and energies, and you can say, is this energy necessary to form the bond, break the bond? Well, we know, because anytime the bond is formed, this is how much energy would be released. To break that bond, that's how much energy would be required, right?
Okay, yeah, that makes sense.
So if I have information like this, I can do bonds broken minus bonds formed, all right? And recognize that these are positive values. So it's energy, again, required to break, or energy released upon forming. So you kind of have to think a little bit about the signs there. But if you just take broken versus formed, or bonds in the reactants minus bonds in the products, right? So now it's different. Usually we go products minus reactants, but because we're talking about positive values here, if you change them all to negative values, then you would do bonds formed minus products minus reactants. Okay, so I'll let you guys think about that in your own minds. But from this sort of a scenario, we can look at a given chemical reaction, look at the stoichiometry. We see that I'm breaking 4 of these CH bonds, breaking 3 of these ClCl bonds. And what am I doing over here?
You're forming those ones?
That's right. What kind of bonds are forming here?
A CCl and a CH.
How many CCLs?
Oh, 3 CCLs and 1 CH.
That's right. And over here?
1 HCl.
Oh, but I have
3 HCl.
Yeah, because they have a coefficient here, right? All right. So I can use this information in the table here and identify how much energy this process would take, again taking the positive values and applying them this way, where we go bonds, positive values, bonds broken minus bonds formed. Okay? So let's try this problem here. Given the D stands for dissociation energy for the hydrogen-hydrogen bond, 104.2 kilojoules, and that nitrogen-nitrogen triple bond is 226 kilojoules per mole. What is the experimental bond dissociation energy for NH3? Well, we can take the number of bonds broken minus the bonds formed and know that that's going to equal, in this case, the delta H for this chemical reaction. All right, so the delta H for this chemical reaction, it happens to be a formation reaction as it's written, is provided here. So we can know that that is going to be the answer, even though we don't know anything about the NH3 bonds, right? We know that bonds broken, those are our N2 bonds, so there's 1/2 of the 226, right? Bonds broken. The other bonds broken are 3/2 of the 104.2. That's my bonds broken. minus bonds formed. There's 3 of these NH bonds. Can you see that?
Because it's NH. Yeah, I can see that.
3 NH3 bonds. I don't know what the energy is for, we could call that our X variable, right? There's 3 of these X's. Bonds broken minus bonds formed, because again, these are our positive bond dissociation energies, will equal this negative 45.9 kilojoules of energy. These are in units of kilojoules here, so we have to make sure we have our same units on both sides. And so I could find out what this is, do the math, divide by 3, and find out what my NH3 is. Okay, you want to try that one?
Okay.
So, everybody at home, try this one as well. Okay, hopefully you took a second to solve it. This is what I got. So it looks like I'm going to get 105. Oh wait, there's 205s. Is it supposed to be positive or negative?
I don't know. Well, yours is a positive, right?
Yeah. Do I know that that's right?
Well, I guess it has to be right?
Well, what are they asking for?
Bond dissociation energy?
All right, so the bond dissociation energy should be a positive number, right? It's how much energy necessary to break, but it's reported as a positive number. So, okay, good. All right, one last problem here. Similar situation. Here's a chemical reaction. We want to know the delta H from the delta H of formation. Calculate delta H from delta H of formation. All right. So we have a similar situation, right? We're going to be breaking some of those sulfur bonds and some of those oxygen bonds, right? And we're going to be forming sulfur-oxygen bonds. So we have to take what? Bonds broken minus bonds formed, or bonds formed minus bonds broken?
Well, isn't it products minus reactants?
Well, you can do products minus reactants, but if you do products minus reactants, then you have to do a negative sign in front of your dissociation energies. All right? If you keep the dissociation energies how they are, then it's bonds broken, which is reactants, minus bonds formed, which is products. Okay? So let's try to keep it that way. I mean, we could have some fun and do it both ways, but I'll let you guys do that at home sometime. Okay? So let's look at the bonds broken minus bonds formed, right? Bonds broken minus bonds formed, using again the dissociation energies. All right, so how many sulfur-sulfur bonds are we going to break here?
Is that 8?
I think so. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And that's energy. What's the energy of a sulfur-sulfur bond?
225 kilojoules for every mole?
That's right. So we got 225 times 8. That's for our sulfur-sulfur bonds. What about the oxygen-oxygen double bonds?
498. And we're going to break how many? Oh, 12 of those, it says.
That's right. So plus 12 times 498. Okay? And now that minus the bonds formed, how many sulfur-oxygen double bonds are going to be forming?
3?
Well, it's 8 times 3, right?
Oh, 24.
That's right. So minus 24 of these sulfur-oxygen bonds. And that is going to equal the delta H for this reaction. We're told that the delta H of formation for sulfur oxide, or sulfur trioxide, is negative 395.2. Now this is not a delta H of formation reaction, is it?
Oh, how do you know?
Well, remember, in a delta H of formation, or a formation reaction, you take enough oxygen and enough sulfur just to form 1 mole of this material.
Oh, okay.
And so here I'm forming 8 moles of material. So if I want to take this much energy, I see I'm given the delta H of formation of 395.2. And again, that's kilojoules per mole. So I know that this reaction here, which forms 8 moles, is going to have a delta H of 8 times that delta H of formation. So I can put here 8 times a negative 395.2 and solve for x. All right? You want to try to do the math there and solve for x?
Yeah, I'll try.
All right, so I have 8 moles of my 225, 12 moles of my 498, and then minus my 24 of my SO double bond, which we're going to call X, equals this 8 times negative 395.2, which is 3,161.6. Finish up the math here, and it looks like each sulfur-oxygen double bond is worth 455.7 kilojoules per mole. Okay, good job, Fred.
All right. Is that it?
That's it for this chapter. See you later.
Bye-bye.